Have you ever felt a shock when you touch a door handle? That little jolt is an example of electrostatic discharge, or ESD, caused by the flow of electricity between you and the handle. ESD is tricky because you rarely see, feel, or hear it happening. It can happen anywhere at any point in time, and the resulting damage can be time-consuming and costly to repair. Not only that, but if you don't know it happened, then how will you be able to fix it before the final product reaches the customer's hands? If a customer receives a product that's been unknowingly damaged by ESD, it could fail as they're using it. At best, this is an inconvenience, and at worst, it could be harmful or even deadly. Luckily, there are things you can do to help prevent it from happening. That's what this course is all about. You'll discover what causes ESD and learn to use the tools, materials, and processes designed to control its damaging effects. In order to understand ESD, it's important to know about atoms. Every object and living thing, from paperclips to planets, to plants, animals, and people, is made of incredibly tiny units of matter called atoms. Each atom is composed of electrons circling protons and neutrons in a central nucleus. Electrons have a negative charge, protons have a positive charge, and neutrons have no charge. Atoms usually have an equal number of electrons and protons, so the negative and positive charges cancel each other out, and the atom is neutral or balanced. Atoms always try to remain balanced. However, atoms sometimes lose or gain electrons. When an atom loses electrons, it becomes positively charged because it now has more positively charged protons than negatively charged electrons. When an atom gains electrons, it becomes negatively charged because negatively charged electrons outnumber positively charged protons. When you run your hand along a rail, dry clothes in a dryer, comb your hair, or otherwise bring objects into repeated contact, something interesting is happening to the atoms of each of the objects involved. Some of the electrons from the atoms of one object may move over to the atoms of the other object, leaving one object with a positive charge and the other object with a negative charge. The buildup of a charge by rubbing two objects together is called the triboelectric effect, because the word tribo means friction in Greek. For example, when you brush your hair with a plastic comb, the electrons move from your hair to the comb. Your hair becomes positively charged because it now has more protons than electrons. The comb, however, is negatively charged because it ends up with more electrons than protons. We call this a static charge, or static electricity, because the charges remain in one area. Curiously, that negatively charged comb can attract other objects like tiny bits of paper. This is simply because opposite charges attract and like charges repel. In other words, negatively charged electrons always move towards positively charged protons and away from other electrons. When the comb is placed near the paper, the excess electrons in the negatively charged comb push away the electrons on the paper. Since opposites attract, the remaining positively charged protons on the surface of the paper are drawn to the negatively charged electrons in the comb. The same phenomenon happens between different objects, even a stream of water. Let's practice. Click and drag the electrons to the atoms so that atom 1 is negatively charged and atom 2 is balanced. Then click Submit. If you need to reset the activity, click the Refresh button. Now, What would happen if atom 1 came into close contact with atom 2? Click the correct response. Because like charges repel, electrons always move from where there is an excess of electrons to where there is a shortage, or at least less electrons than their original location. In other words, an object with too many electrons wants to get rid of them and go back to having the same number of negatively charged electrons and positively charged protons. In scientific terms, we say that a charged object has electrostatic potential, and when possible, its excess electrons will flow to an object with less electrostatic potential, so that both objects are at the same electrostatic potential. For example, if you slide a metal pair of tweezers across a formica table, it will become negatively charged. The tweezers now have a higher electrostatic potential than a component with a neutral charge. Therefore, the tweezer's excess electrons will jump to the component in an ESD event as soon as they come in contact. We've seen how the triboelectric effect can cause a buildup of static electricity on people and objects and lead to damaging ESD events. But not every object you work with is created equal. All of the objects you touch fall into one of two categories: conductors and insulators. Conductors are materials through which electrons can easily move as an electric current. Most metals and some liquids, such as sweat, are good conductors. Everyday examples include metal tweezers, the metallic tips of a soldering iron, and even you. Insulators are poor conductors of electricity because they resist the flow of electrons. Common insulator materials include the plastic, styrofoam, and rubber used to make everyday objects, like water bottles, tape dispensers, coffee cups, and plastic bins for holding your parts and tools. The important thing to understand is that electrons move and behave differently in conductors and insulators. Conductors, such as these metal tweezers, have many free electrons that can be made to travel in the same direction as an electrical current. On the other hand, insulators have much fewer, if any, free-floating electrons, and they do not move easily throughout the object like they do in conductors. These characteristics of conductors and insulators make them behave differently when it comes to ESD. For example, because the electrons of a conductor can move easily, the electrons in a negatively charged pair of metal tweezers will jump over to an electronic component at the first possible opportunity and cause an ESD event. The process is a little different with insulators. Let's say you're negatively charged, and you reach out and grab a plastic water bottle. Because people are relatively good conductors, your excess charge will jump over to the bottle. However, the charge will remain at the point of contact because electrons do not move easily through insulators like plastic. If that water bottle comes near an electronic component, the negative charge won't jump over and create an ESD event. Instead, the negative charge on the bottle attracts the component's protons and repels its electrons. This causes one end of the component to become negatively charged. Scientists call this phenomenon induction. Now, if a conductor, such as our metal tweezers, contacts the negatively charged portion of the component, it will cause an ESD event and most likely damage it. How would the protons and electrons of this electronic component react if they came in close contact with this negatively charged plastic water bottle? Click the correct electronic component. What is this phenomenon called? Click the correct response. Now that we know a bit about atoms, let's review what we've learned. Everything in the universe, including you, is made of atoms, and each atom is composed of electrons, protons, and neutrons. When you walk across a vinyl floor, the triboelectric effect causes electrons from the vinyl to move through the soles of your shoes and into your body. Your body's atoms now have more electrons than protons, so you are negatively charged. Because opposite charges attract and like charges repel, when you reach for the door, the excess electrons on your body repel the electrons on the door handle and attract the protons. The door handle's atoms are balanced, but you are at a higher electric potential, so your excess electrons jump through the air towards the remaining protons in an electrostatic discharge. Clearly, a zap from a door handle may not hurt you, but electronic components are especially vulnerable to even small amounts of electricity. In fact, a person walking across a typical vinyl floor can generate as much as 12,000 volts of electricity, which is 50 times more the amount necessary to destroy an electronic component. The size, construction, and materials of an electronic component all play a role in how sensitive it is to ESD damage. As components become smaller and operate faster, the sensitivity increases. The most vulnerable of these are called electrostatic discharge sensitive, or ESDS components. There are two types of ESD damage: catastrophic failure and latent failure. Catastrophic failure is dramatic and obvious because the damaged component immediately causes the product to fail. Latent failure is when an ESD event damages a component but goes undetected because the component still works. However, the damage worsens and eventually causes the product that incorporated the component to fail. Latent failure is often worse than catastrophic failure because a defective product can cause serious injury. Defective products are costly to repair and damaging to the reputation of the manufacturing company. What is likely to happen when you walk across a vinyl floor? Click the correct response. If you are negatively charged, what kind of electrostatic potential do you have compared to a neutral or balanced electronic component? Click the correct response. If you have a higher electrostatic potential than the component, what will happen when you try to grab it? Click the correct response. Let's practice. Drag the tweezers to the electronic component indicated by the circle. Oh no, there was an ESD event. Now, if this same assembly failed inspection, would that be an example of catastrophic failure or latent failure? Click the correct response. Now let's say that same assembly actually passes testing. Does that mean there is no problem? Click the correct response. ESD events cost the electronics industry billions of dollars each year in component replacement costs, customer service, and field service time. As if that weren't bad enough, ESD damage is often partial. The affected component or assembly passes inspection, is shipped out, and then fails when it's in the user's hands. As you might imagine, this makes for some very unhappy customers, and a large enough number of dissatisfied customers can quickly lead to a decline in sales and even layoffs. Therefore, it's important for everyone to do their part to control the effects of ESD. Let's apply what you've learned in this module. The rules are simple. There are 6 questions in this game. You have 10 seconds for